So, this first lesson has been about mechanical waves, really. Remember what, I know I told you, do you remember what I mean by mechanical waves? Do you remember what I meant by mechanical waves? No? No? These are the waves like the ocean waves, sound waves, the earthquake waves. What do they have in common? They need a material. Yeah. So we call this mechanical, like mechanics. Mechanical. The waves we're going to look at now don't need a material, like light, X-ray, you said, microwave. They don't need a material. And these have a special name. That's it. These are called electromagnetic waves. Oh yeah, sorry, I'll get it up now. There we go. Electromagnetic waves. I'll make sure I'm recording. Okay, so we have been doing some talking about waves, but we haven't really talked about how you can tell if something's a wave. If something is not a wave, then what do we call it? So we have things which are waves, and then we have things which aren't waves. Like, for example, you are not a wave. I am not a wave. This is not a wave. So what do we call something that's not a wave? Particle. So something which is not a wave, we call it a particle. Yes. Well, no, that would be in semester 2. We won't get into that yet. And it's not really controversy, it's just confusing.
It was recently this was discovered that these technically those.
Oh, that's not recent. I'm sorry to tell you this. This would be this would be about 80 years old. The fact that you mean that recent?
No, it was just like I read somewhere where it was being discussed again.
Again?
To determine exactly what light is.
No, I think the question's been answered. So I tell you this. Yeah.
Loves.
Yeah, that's semester 2. We're going way ahead of ourselves. We're talking about semester 2, yes. So something is not a wave, it's a particle. So how can we tell if something is a wave or something's a particle? So we can do the following with 2 slits. Okay? Yes. If something is a wave, when it hits the 2 slits, it will come out of the 2 slits, and then on the screen you'll get on a wall or a screen you'll get places where the wave hits a lot, like in 10 spots. If it's not a wave, if it's a particle like a person, so what happens when you run through one of these slits? Yes, you just go here, I'll do it in red and everything. You just go splat in one spot, isn't that right? Whereas a wave, like picture water, if water goes through 2 holes, then it will come out of 2 holes, okay? Whereas if a particle goes through 1 hole, it will come out of 1 hole. So if you want to know if something is a wave or a particle, all you have to do is send it through 2 slits and see what happens, okay? So if you have light, and you send your light through 2 slits, and you look at what you get some light here, and you get some light here, and you get some light here. So is this a wave, or is it a particle?
Wave.
It would seem like it's a wave. And for the moment it is a wave. Okay, for the moment it's a wave. So light is a wave. But it's a very special type of wave. What's special about light as a wave? Do we know? What things are special about light? Well, like I said earlier, it doesn't need any material to travel in. It just travels. So it could travel in space, in a vacuum, no air. It could travel underwater. It could travel in this room. So the first thing about light is an example of a electromagnetic wave. So what do I mean when I say electromagnetic wave? Well, these are very, very special types of waves. First thing about an electromagnetic wave is it needs no medium. So it doesn't need any material. It can travel in space, it can travel in the room, it can travel anywhere. It doesn't need a material. Another thing that's important about electromagnetic waves is that in a vacuum, its speed is, and I can't stress this enough, always equal to c. c is called the speed of light, and it's roughly 3 times 10 to the 8 meters per second. Huh? Speed of sound is about 350 meters per second.
What's the symbol for C?
For what? Speed of sound? We use V. We could use C, but we use C for light, definitely.
So I'm just thinking of the one of the FC over C and CU.
Oh, yeah, sometimes letters are reused. I think that might be a C0 though. Anyway, it's really fast. 10 to the 8 meters per second is huge. Like how big is a kilometer? 10 to the 3. So how big is 1,000 kilometers? 10 to the 6. So this is 300,000 kilometers per second. So it's really, really fast. Okay. And other things that are important about it. We can say that, now this is something that we'll talk more about in semester 2, but the energy, do you remember we were talking about energy for ocean wave, and we said it's important to know how big the wave is, because if the wave is really big and it hits you, that's a lot of energy, yeah, and of course how fast the wave is moving as well. But for electromagnetic waves, it doesn't matter how fast it's moving because it's always the same speed, and it doesn't actually matter how big the amplitude is as well. For electromagnetic waves, the energy only depends on the frequency, which is very strange. This is not true of ocean waves. You know, if an ocean wave is bigger, then it has more energy, if it's higher. Okay? But for light, electromagnetic waves, it doesn't matter, it just matters about the frequency. Okay? So light is an example of electromagnetic waves, but there are many, many more types of electromagnetic waves. In fact, let me get it up here, the diagram I want. What the heck? Give me my chart. There we go. How can I know. I'll save it on the desktop and then I can zoom in. Preview. where are we? Where's our light? Here's light. So, Abraham gave an example of X-rays earlier. Have you ever been to the hospital and gotten an X-ray? Yeah, some people have. Yeah. Louise, have you? Yeah. Believe it or not, X-ray and light, you see the light here, they're the same thing. They're exactly the same. That's the light here and the X-ray in the hospital, they're the same thing. The only difference is the frequency. So in this diagram here, you can see that the frequency here, or sorry, another way of saying it is that the wavelength is different. Can you see? You see the light bulb? Here's wavelength. Here's wavelength. Light bulb is around about, what's that? 10 to the minus 6 meters. So light is a really tiny wavelength. Like the distance between the crest and the trough is really, really small. What happens when the light gets a smaller frequency, a smaller wavelength? Then look at the very end. Do you see where it has, I can't see it. See that robot there? Here. Yeah. See this guy here? That's X-ray, okay?
That's people.
No, it was a person behind the X-ray machine.
Beside the light bulb.
That's people, yeah.
That's people. Okay.
I don't know why they're there. They're not light.
Yeah.
There's a light bulb here. That is 10 to the minus 6. The X-ray is 10 to the minus 10. You see that? Now what happens when we make the wavelength bigger? Well, then your light turns into radio, microwave, this is radar. Radar, microwave, radio, and then at the very end there's AM radio. Now what this graph is missing is your mobile phone. Your mobile phone would go around about where did I put it?
Just after radar.
No, I don't know if it's, hang on, let me just think here. I know that it is, I think it's just between radio and microwave. This is where your phone goes. So, it's really hard to picture this, but when I call someone here, what comes out of this phone? The wave. But it's hard to imagine what's coming out is a light wave. Light wave is coming out. But why can't we see it? Yeah, we can only see a small part of this with our eyes. The only part we can see with our eyes is this piece around about here in the middle. We can see the light waves if they're this frequency, but when they get bigger or smaller, we can't see them.
Better into visible and then ultraviolet.
Yeah, ultraviolet, visible, and then infrared. So there are waves around us all the time. There's light waves, and then there's light wave coming from my phone, and also Wi-Fi. Wi-Fi is no, not infrared. Does anybody know where Wi-Fi, internet Wi-Fi would go here? Correct. The wavelength for Wi-Fi is the same as the wavelength for microwave. And you know how you can check this? If you put your laptop in the microwave, yeah? Don't turn it off. If you put your laptop in the microwave and close the door, then you lose the signal. Because the door on the microwave is made so that the microwave can't come out. So this means that the Wi-Fi can't go in. But it's funny, if you take your phone has Wi-Fi and telephone on it. So if you put your phone in the microwave and look at it, you'll see that it still has a signal, it can still connect, but it has no Wi-Fi now. Because it stops the Wi-Fi, but it doesn't stop the telephone pole, the telephone mast. Okay? So my point is there's these electromagnetic waves everywhere, and all they really are just light waves, but they all have different frequencies, different wavelengths. So what we need for the exam is we actually need to learn the order, which is the biggest wavelength and which is the smallest wavelength. So I'll try and find a better picture here, because this one is a little bit too much on it. I want something simple but not too simple. Don't do this to me.
She's not been forward.
Oh yeah, no, this will do. This is exactly what I want here. Okay. So here are wavelengths. So here is 300 meters, that's radio wave. And it's radio wave if it's 300 up to around about 30 or so, 3 meters or so. Now these are centimeters. Can you see that? Centimeters. So between, here's 3 centimeters, here's 30 centimeters. So, I don't know, around about maybe 6 or 7 centimeters. That's to round about maybe 1 centimeter. That's microwave. Now infrared, does anyone know what infrared is? No, infrared is what your remote for TV. That's infrared. Okay. Now you all know X-ray for the hospital. Does anyone know gamma? Gamma? Yeah, it's the whole question is.
Yeah.
Do we know gamma outside of DC Comics or Marvel?
Gamma rays.
Gamma is only really in space. It's only in space, really. Okay, it's not so much on Earth. Now, there's a very, very, very important one there for health. Ultraviolet. Does anyone know what ultraviolet is? You know ultraviolet, yeah? Do any of you guys know ultraviolet, this word? Yeah, what is it? Is it a good or bad thing? Yes, you're right. If you get too much ultraviolet, it's bad for you. It can cause, what can it cause?
Cancer.
Yeah, what type of cancer? You do know. What type? Skin cancer. Ultraviolet is the light that you get, it comes from the sun. And if you stay out in the sun, it can burn and damage your skin. It's the ultraviolet that does this. Also notice the visible lights are different colours, have different wavelengths. Remember we were talking about sound and you said different frequency. So low frequency, high frequency. The same is true for light. If you have a big wavelength, that's a red colour. And if it's a small wavelength, that's the violet colour there. Now, what I'll do is I'll write this down here. For the exam, they sometimes ask you to list all of these in order. Before I do that, what's the formula for speed of a wave? V equals F lambda. But what's special about electromagnetic waves, about its speed? It's always C. So if I make the F bigger, what happens to the wavelength? It must get smaller. And likewise, if I make the F smaller, what happens to the wavelength? It gets bigger. So you see here, here is a big wavelength, so that means it is a small frequency. And here is a small wavelength, so that means it is a big frequency. Okay, so we need to write these down, but I need to see them to write them down. Maybe you can write them down. So what you can do is make, just draw this. But don't worry about drawing the wave. I just want the names, okay? So start off with, well, hang on, hold on. Large, let me show you what I want. Wavelength, or in other words, small frequency. And then here, small frequency. No, I know. Don't confuse me. Small wavelength, large frequency. Okay. So I want you just to have it looking like this. So you can list them here. Like first you have, what was first? Radio, wasn't it? Okay. And then what's after radio? We have radio micro radio. Microwaves. And beside, underneath microwaves, what else can you write? What's the same as microwaves? Wi-Fi. Yeah? Wi-Fi, yeah, what are you going to say? No, in fact it's the same. Same, yeah. After that, I think after that we can maybe have, radio. Don't forget to have mobile phone. Mobile phone is after radio and before microwave, and then we have Wi-Fi, then we have infrared, then we have light, then we have UV, X-rays, and then gamma. Okay, so I'll show you here on mine. We have radio, we have mobile phone, we have microwave and Wi-Fi, then infrared, then visible light, then ultraviolet, then X-rays, and then gamma rays. Okay, you got that written down? Now you do need to remember this for the exam because they have sometimes asked for you to put these in order. But they don't, I think they leave these two out, phone and Wi-Fi. Oh yeah, and light also, we need to know the colours. So which colour has the, well, actually, look, it's very easy to remember because what's right before red here? What's before light here? Infrared. Does anyone know this prefix infrared? Infrared means just before red, and ultraviolet means just after violet. So the colours here go just like the rainbow. Do you all know your rainbow colours? Wait. Let's get the non-native speakers to give me their colours. What's the first colour of the rainbow? What's first colour? Yeah, red. First colour, red. What's next? Red. Orange, very good.
Yellow.
Very good.
Green.
Oh, great.
Blue.
Oh, great.
Purple.
Now you skipped one. It's a purple colour, but we don't use the word purple. Yeah. It's called indigo. And then Ibrahim, what's the last one? Violet. Yeah, violet. Yes, violet. So look, infrared is just before the red here, and then ultraviolet is just after the violet at the end of the light colours. Okay. I feel it's important also to talk about health now as well with this. Some of these are bad for your health if you have too much of them. We already talked about one. Which one is bad for your health if you have too much? Yeah, who was saying UV light causes skin cancer? So this one here is bad for your health. What else is bad for your health if you have too much? X-ray, yeah. And then of course here, the last one. Is light bad for your health? No, of course not. Yes, we would all be dead there. Infrared? No. Microwave and Wi-Fi? Mobile phone? A little bit. Now this is the point I'm really making. The answer here is no, 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 and no. There's this idea sometimes, and I know why people say it, that microwave and Wi-Fi and mobile phone is dangerous for your health. It definitely is not. And the reason it's not is because the electromagnetic radiation is not dangerous until you reach this part of the graph. So here is 100% safe, and then here this is where we could have a problem if we have too much of it.
So where does the mentality come from?
I don't know. I'm sure you hear this in your home country too, that if you use your mobile phone too much, it's bad for your health. Have you heard this before? Yeah, this is completely not true. It is 100% wrong. Completely wrong. Yeah, no, it's completely wrong. And sometimes people say the same thing about Wi-Fi. Again, it's 100% wrong. It's 100% wrong. Because if you say these are dangerous, then these here must be more dangerous. Are these more dangerous? Well, no, because it's like Ugo said, if light was dangerous, then we'd all be dead. So the thing about electromagnetics is it gets more dangerous as you have a larger frequency or a smaller wavelength. So a larger frequency makes it more dangerous. There's a frequency here when it starts becoming dangerous for people, and I need to get the values because I think you should know what it is. I think it's called like the threshold frequency. No, threshold frequency. Yeah, it actually might have other meanings. Hang on, I know what I'll type in. UV type 1. Tannin, yes, is very bad for your health. I want the number. 10 to the, what's that? 10 to the minus 6, yeah. Sorry, I should have written the numbers in here as well. This is 10 to the minus 6 meters is the wavelength here.
So we need to remember the wavelength.
We draw it and then tell you to put the...
No, you don't need to remember them, but it's good just to kind of roughly remember them. So for example, for light, its wavelength is it'd be one bigger than this. It'd be about 10 to the minus 5 for light. Ultraviolet would be 10 to the minus 6. These ones here would be 10 to the minus 7, minus 8, minus 9. Infrared, let me see, what's that? 10 to the minus 2.
Wait, Stephen, I'll make sure that it's meters.
Oh yeah, these are wavelengths, so these are meters, yeah. Radio can be really, really big. Like radio can be up to, in fact, radio can be up to 10 to the 3 meters, like a kilometer. It's huge wave. Okay. Oh, sorry, I realized I was writing here. Yeah, so light is, 10 to the minus 5, infrared, minus 2. Now, who you asked me, do you need to remember them? No, but you need to at least roughly remember them. So, for example, if you had a 10 to the minus 7, minus 8, you should know that's not light, that's like an X-ray. And if you had something really, really big, like 100 meters, that would be radio. Microwaves tend to be around about, 5 centimeters. Maybe this is like 4 centimeters, something along the lines of centimeters, 10 to the minus 2. Maybe a little bit bigger, sorry, maybe more like maybe 15 centimeters. It's not important to remember these, it's just good to get an idea of the scale. Next now. Idea, polarization. Does anyone know this word for waves? You might know, Joe.
Yeah. Polarized.
So we have two types of waves, remember? Transverse and longitudinal. It's actually possible to change a longitudinal into a transverse. What you do, you have a special, well, not actually special, some kind of barrier, and this barrier has a very, very small gap in it like this. And what happens is, when the longitudinal wave comes along and hits this, only a small piece can be freed. And when it comes out, it can only be a transverse because it's so small it can't spread out. It is like you're cutting a slice out of the longitudinal and you're left with a transverse. This is called polarization. Polarization is changing a longitudinal wave into a transverse wave. That's polarization.
So we need to cut off. Cut off.
Yeah, it's like most of the wave gets cut away and you're just left with this little transverse piece. Yeah. Because what happens is it gets stopped by the wall, except a little piece comes out. This, I believe this is what they do for radio waves. When, like a radio station, they polarize the radio wave, so it is like this. Now, I think the reason for that is it can travel a greater distance. You don't have to worry so much about buildings and hills. I think they probably do the same thing with TV. So anyway, the point is, this is a process. It's a simple process, but it's done for radio and TV and things like this. Polarization. Okay. Huh? Sunglasses, yeah. And there are special, really good sunglasses, and what they do is, if you look at the sunglass, it looks black, of course, and it's actually lots and lots and lots and lots of little gaps. And when the sunlight comes in, as a longitudinal, it comes out as a transverse. Now, why is that useful? Well, think about it. Most of the wave does not travel through the sunglass. Only a little piece travels through the sunglass. So it makes it look darker. If you had another one of these sunglasses and you put them together, except you put them like this, maybe I can show you here, yeah. So imagine you have two of these sunglasses, but then I turn one of them sideways like this. Then you get no light. Why do you get no light if I have them like this? Can you see that? So for example here, the light comes in, and then when it comes out, it's only going up and down, up and down. Everything else is being cancelled. So if I have it like this, what happens is the light goes in, goes up, down, up, down, up, down, and then when I hit this one, just continues, up, down, up, down, up, down. But then, yeah, if I turn it sideways, like this, the light comes in, it goes up and, then it goes up and down, but when it hits this one only lets the left-right come out. Is there any left-right when it's only going up, down? No. Yeah?
Between the two glasses, the we have to gap.
Oh, in my example, yeah, sorry, I should be clear. So imagine I have my two sunglasses, I take them off, I break it, and I put them on top like this. So what I'm saying is if I keep them up and up, then it's fine, there's no problem. And if I turn it sideways, this one, then I get no light, it's black, I can't see anything. And what's happening is, this light that comes in leaves going up and down, but then when it hits this one, it can only come out as left and right. But is there any left and right if I'm just going up and down? No, there's not. So for example, if I just have this, and the light hits it, it comes out as left, right. Then if I turn it this way, it comes out as up, down. I'm just saying if I put them together, but I turn one of them, it's black. And then if I turn it back, I can see again. That's all. Now, I don't know if anybody has these glasses. They're expensive, so if you have expensive glasses, they're probably like this. Anybody have expensive sunglasses? Yeah. Yeah. If you have two pairs of them, you could check them. Or you could break one pair. Your choice. Okay. I need another picture here for you. Anyway, this is called polarization. So, can you copy this picture now for me? We can talk about it. Yes, I'm sure you all remember this from, maybe you remember this from middle school or high school or something. So what happens here, I'll draw it for you. Here we have some glass, just regular glass, but it's shaped like a triangle shape. And here we have white light. And what I mean by white light is light from the sun. Okay. So it has no colour really, it's just white. When this light hits the glass, it splits, and then you can see all the different light inside of the sun's light. So here we have red first, I don't have orange, yellow, green, blue, blue, indigo, violet, and so on. The idea here is if you have red plus orange plus yellow plus green plus blue plus indigo plus violet, if you put all of these lights together, you can make white light. But the opposite is true. If you have white lights, you can separate them into all their different colours. Have you seen this picture before? This picture here. You've seen this before? Yeah? Who did this? Which person? This is experiment. Who do you think? Who did this? The person, yeah. Like, who was the first person to do this with light? To discover that white light can be separated into all the different colours we can see.
Do you know this person?
I know this person. Not personally. Quite old. Big man. Important guy. Likes apples. Newton, yeah. Newton was the first person to do this, I think. Yeah, I think so, yeah. This is Newton. I thought it was Newton. Newton put white light through a glass prism and it separated into the different colours. Because you can see this with a rainbow.
Yeah, that's what I thought.
Yeah, like how does a rainbow work? A rainbow works because when there's water in the air from the rain, you know what rain looks like. The light comes in and it hits the rain and then it spreads out into the different colours. So this is how we get the rainbow. Because the water is like the glass. You know, it's the same effect. Yes, okay, next now. Try and draw a nice example here. So we have clouds, and then the rain is falling, and then we have our sun at the same time, and the white light hits the rain, and then it spreads out as red, green, blue in the sky, and we get the rainbow. You know what a rainbow looks like. Okay. Tell me, in chemistry, what are you doing at the moment? What chapter? What topic? Halogens. Gas or something. Yeah. Yeah. What did you do previously? Well, what I'm wondering is, have you done anything to do with spacing, like the spectrums, like line spectra, emission spectra, absorption spectra, but you haven't done it in chemistry. Yeah, you will do it in chemistry. Okay, so next part of this, can I go down? Yeah. So we have, now we're going to talk about spectrums or spectra. Emission spectrum. Think about the guy who started. Think about coal. You all know coal, like in a fire. So when the coal gets really hot, what colour is it? Yeah, maybe yellowy, maybe red, something like this. Yeah. Everything that gets hot will start to glow. So coal starts off black, but when you heat it up, what colour comes out of it? A red, yellowy colour, yeah? But this is true for everything. So like, for example, you know, if I took like this metal here, and if I made it really, really, really hot, it would start to glow. Light would come off of it. Okay, this is true for everything. So, for example, you all know hydrogen, of course. Hydrogen. You did this in chemistry. It's the first element. So imagine now we had in our container here some hydrogen, and we apply some heat here, and we keep applying heat until it starts to glow. What will happen is we'll get some colours that will come off of it. You know, maybe some red, I don't know, maybe some blue, who knows? Some colours will come off of it. What you can do is you can look at these colours on what's called emission spectrum. Basically, this is an emission spectrum. Here you have red, orange, yellow, green, blue, indigo and violet. So if you get red light, you can colour in what frequencies of red light you get, so maybe you get some red light. And if you get blue light, then you can colour in what parts of the blue you get, for example. Okay. what do we say about coal? For example, coal maybe is like red and orange. Now, you know there are many different shades of red, shades of blue. You know, it's not just one red or one blue. So for example, with the red here, maybe you get only these colours of red and these colours of red, but maybe not the colours in the middle. And the same goes with blue or whatever. And who knows, maybe you get a little bit of yellow, a little bit of orange, a little bit of green, a little bit of each. This is called an emission spectrum. And what's really, really great about this is that it's different for every material. So everything has a different emission spectrum. So the emission spectrum from this is different to this, it's different to me. If you heat me up, I will start to glow. That will be different colours than if you heat this up. Okay? So the important point here is, well, right at the top here, emission spectrum is different for everything, for each thing. Now I'm saying that this is important in chemistry because this is how we can tell what is inside of something. You know, if you have something in chemistry and you don't know what it is, what you do is you put it into this tank and you make it really hot. And then when it's really hot, it starts to glow and different colours come off. And then you have a computer, and the computer makes this emission spectrum. And then the computer can look at this and go, oh, okay, I've seen this before. It looks like it is carbon, hydrogen, and oxygen, something like this. So this is great. It's great that everything has a different spectrum, because it means no matter what you have, if you heat it up and look at the light that comes off of it, you can know what it is. So it's a very, very useful result, especially in chemistry. Maybe I can find some online example pictures here. Let's see, emission spectrum. Does Katy Perry have an album called Prism or something? She must do, because yeah, so here's the heat the gas and it gives it off there. Oh yeah, you can use, I said in my example, because it's been very modern, you can use a computer to make the emission spectrum, but the old-fashioned way was to have a prism separate the light out. No. Let's see, the planet one here. Yeah, so for example, if you were to look at the sun, you know, it'd be mostly yellow. Oh, that's not a good one. I know, emission spectrum of hydrogen. Let's have a look. Oh, great. Here's three. Can you see those materials? Yeah. So look at hydrogen. For hydrogen, when we heat it up, we get a little bit of blue light and a little bit of green light here and a little bit of red light. I don't know if you can see this, but up the top here, can you see that? That's wavelength. Here, I'll save it. Where's preview? Can you see this there, wavelength? So you have a little bit of blue, a little bit of blue, a little bit of green, a little bit of red. And what's Hg? Sorry, it's what's Hg? Hg is it magnesium?
No, it's not.
Helium? No, helium's He. Hg is Mercury. Yeah, okay. And Ne, that's neon. So for Mercury, you get red, green, yellow, orange. Red here. blue here, green, yellow, orange. And for neon you get these different colours. But if you had a gas that was a mixture of hydrogen, mercury and neon, then the spectrum you get is like if you put the three of them together. Okay? So first, can you imagine in your mind, you put the three of these together onto one? That's what you would get if you had a mixture of the three. Okay? And you can see how they're all different. Let's see what I would be. So what are people made of? Carbon, yeah. So let's see if I can get carbon. And some hydrogen because the water, and some oxygen. I don't have it. Okay. Do I have? Maybe I should write in carbon. Yeah, here we go. Right, so it looks like it's mostly a green colour. So if you heat me up until I start to glow, I'd be mostly a green colour. It's good to know. Yeah? Because you can see green is the most common light colour coming off there. Little bit of blue, little bit of red. Anything else we can heat up? Oh look, here we can have a look at a few of them. Can you see this view image? So hydrogen looks like it's just really kind of a greeny colour mostly. Neon looks like you have more of a mixture. Anyways, I'm talking too much about this. I think we all understand the idea here of emission spectra. Yeah. There's just one other thing to say, which is something really peculiar about the sun. So the sun, what's in the sun we look at? Does anyone know what atoms make up the sun? Hydrogen and helium. Yeah. So if you were to look at the sun and look at the emission spectrum, it would look like it's, I mean, the sun is mostly yellow, isn't it? Red, green, orange, yellow, green. Sorry, I'm tired. Red, orange, yellow, green, blue, indigo, and violet. So if you look at the sun, you get mostly yellow colour. But I think it's important to point out that you don't get all the yellow colours. It's actually really strange. You get all of the yellow colours except for two, which is really, really peculiar. If you look at the sun, you get all yellow colours except for two. Okay, and these gaps have a special name, which is called I think they're called Fraunhofer lines. Now the reason there is a gap will become clear in semester 2. There actually is a good reason that there is a gap. F-R-A-U something, U-N-H-O-F-E-R. So for some reason, the yellow light at those two places does not leave the sun. All the other colours of yellow leave the sun, but those two colours of yellow don't leave the sun. And there's a reason for that. I wonder if anyone knows it. I won't tell you until semester 2, but I wonder if anyone knows the reason. No? Okay. So there is a reason for it, which we'll learn about in semester 2, but we get all the colours except for 2. Okay. Right, let me see. Anything else to mention about this? No, I think that's enough actually. Now, the questions here, again, there's actually 0 calculations in this lesson. I don't need you to do all of them, but I would like you to do some of them. So can you just mark these ones, please? I'll call them out. Oh yeah, definitely try to do number 7. Number 8, 9, 10, 11, 12, 13, 14, 15. 8 to 15 will do the job. So 8 to 15. They're very short.
8 to 15.
Number 7 to 15. 7 to 15. Actually, you know what? Let's make our life easy. Let's do them now together. We can just...
Okay.
We can do it.
So they're in here.
Yeah.
There's no numbers, but...
7. If a body reflects no light, so if you have no light coming from something, what colour will it look like?
Black.
Yes, right. 8. Compared with the speed of radio waves, is the speed of light more than twice, much greater, but not twice as great, almost the same, much smaller, or less than half?
Compared with radios and speed.
Compared with the speed of radio waves, is the speed of light more than twice, much more than twice, or not more than twice, almost the same, smaller, or less than half? Oh no.
Well, in air,
No.
I was thinking of the back.
Yes? Yes, A. Much faster. Radio waves are much... Oh wait. Oh sorry, I'm wrong. I'm so sorry. Yeah, sorry, I mixed up sound, sorry.
Yeah.
Radio waves and light waves. The answer is C.
Yeah.
In fact, I wouldn't say exactly the same.
Yeah.
Exactly the same, not almost the same. Exactly the same. Okay, which of the following have the shortest wavelength? Radio, gamma, infrared, visible, or microwave?
Gamma.
Yes. Maybe we can let someone else do the next one, yeah? Because I know you probably want to go home quickly. 10. Visible light waves differ from ultraviolet waves. Why or how? Is the reason that they're different because one is more slower, one is quicker, they don't need a medium, they vibrate transversely or have longer wavelengths. What's the difference? Or is there a difference? Yes, do visible light waves differ from ultraviolet? Yes, they are different, of course. How are they different? Yeah. Visible light has a longer wavelength than ultraviolet. Yeah. 11. Which of the following has the highest frequency? Let's go with Louise for this one. X-ray, is that the biggest?
No.
Yeah, there's no gamma there. Yeah, X-ray is the biggest frequency of all of those. Correct, yeah. And then, Abraham, let's see. Which of the following cannot be polarized? Yeah, no, I think he's right actually. Yeah, because I think polarization, you can only really do it with light, with electromagnetic waves.
The rest of them are electromagnetic.
Yeah, you can't polarize sound waves, Ugo, because what happens with the sound wave is, well, just think about it. Like, if I talk through a narrow gap, you can all still hear me, so the wave will still spread out. Yeah, the question is not a good question. Basically, it's electromagnetic waves that can be polarized.
Because I know sound waves can be cancelled out.
Oh, they can be, that's true, yes, they can be, and we'll talk about that later too. Which of the following lists them in correct order of increasing wavelength? Yeah, which one is that? So the wavelength gets bigger. Yeah, it's either going to be A or B because it has radio waves at the end, which is the biggest. Is it A? Yeah, so it is A. Give me two properties of infrared. Give me two features of infrared.
It's not visible.
Correct, you can't see it. Yes, what else? Yeah, go ahead, who?
It's visible. It's not visible and it is visible.
Yeah, go ahead, who? Give me something else true about infrared. So you can't see it.
As
I think that the wavelengths are frequency of it.
What? Say again?
Can I say the wavelength and frequency of the infrared?
I agree.
Nah, give me a property. Give me a feature.
It has a larger wavelength.
No, you're complicating. You're complicating. What's the speed of infrared?
The light speed.
Light speed. Yeah, so there you go. That's something else. What about for ultraviolet?
It's not visible.
It's not visible? Ah, yeah, we're trying to do something different this time. You're right. Yeah, thank you. It's unhealthy, yeah. It can travel through a vacuum. Its speed is light speed. Yes, it's unhealthy. You can't talk to me,
Emitted by the sun.
True, the sun admits it. Yeah, that's all I really need you to do for this. So we're just talking about electromagnetic waves. And how many people have a microwave at home? Microwave. You have one? You have one? You have one? How many people have Wi-Fi on their phone? Yeah, Wi-Fi.
Yeah, everyone else.
Yeah.
You should be lost and all, like the kind.
How many people have Wi-Fi in their room? So you can see if you have a Wi-Fi signal. Yeah. So when you go home, please do this. Really, please do this. Yeah. And this is what I want you to do. Show me your phone. Can you show me where it says if you have a signal or if you have Wi-Fi? Yeah. So you see here, you have Wi-Fi and mobile phone. So you put this in the microwave, put it standing up, make sure the light's on, close the door, and look in at the screen. You will see that you will still have a mobile phone signal, but you will now have no Wi-Fi, because the door stops the Wi-Fi. Try it. It's true if you can do, if you can fit your laptop in the microwave also, you can see that the Wi-Fi signal disappears when you close the door. Please don't turn the microwave on.
Yeah, when you said it first, I was like, why would we do that? You know what it's showing?
What's that?
No, what was it?
You will break your phone for sure.
Yeah, it's like, like a restaurant where you can show you're doing with vibrating.
Your phone will slowly melt and cook away in the
If you
microwave.
put in one of the big screens, the screen cracks or something.
I think the reason screens crack simply is because it heats up and expands.
Yeah.
But I would be worried about the battery exploding.
I think the screen cracked before the battery explodes.
Yeah.
So basically, at that point, I think you did click.
Yeah, or just not put the phone in the microwave and turn it off.
Well, probably.